Alright, hey guys, what's up? I'm currently recording at 4:23 in the morning. This is problem number 4 from your final number 2, so if you can go to that, or if you want to take out a new piece of paper, you can do that. I'm also going to be putting a blank file for number 4 online if you want to print that out. Alright, so for part A, oh, and you guys did really good on number 4. Ben got a 9, and Rochelle and Arrow, I think you got like a 4 or 5, so everyone was passing on this problem. Alright, so average acceleration, most people got this one, but the average of anything is equal to 1 over b minus a integral from a, that's a bad integral, let me try again, integral from a to b of that anything. So if I'm looking for average acceleration, then I need to be putting acceleration here, or the integral of acceleration. What is the integral of acceleration? Is it position, velocity, or acceleration? And you should be saying yes, it's clearly velocity, Mr. Sindel. So if I put here, I can write this out a little bit more. This is not going to be equal to, well, so average acceleration is equal to 1 over, so 0 to 80, so it's going to be 80 minus 0, integral from 0 to 80 of acceleration. And that is going to be equal to 1 over 80 times, and then if I take the antiderivative of acceleration, I'm left with velocity. So it's going to be v of t, evaluation bar between 0 and 80, 0 and 80. And therefore, if I plug in 80, plug in 0, if I plug in 80, I get 49. So it's going to be 49 minus, when I plug in 0, I get 5. So 49 minus 5, all that's divided by 80, or 80 minus 0 if you want to keep leaving it like that. And some people, you can just skip to this step if you want, because average acceleration is the secant line from 0, 5 to 80, 49. And if you skip to that point, perfect, that works out. And simplifying this a little bit, so that's going to be 44 over 80, and then I'm going to divide the top and bottom by 4. That's going to be 11 over 20, and it says to indicate units of measure. So units of measure, it's going to be, we're now talking about velocity, right? So velocity is measured in, or sorry, no, it's average acceleration. So average acceleration should have units of acceleration. It's like, what's the average number of cards? It's 3 cards. So the same units for whatever I'm talking about. So the unit of acceleration is feet per second per second. You can write that a few ways. You can say feet per second squared, or you can say feet per second, whatever works for you. All right, on to part B. I think everyone got full points on A, if I remember correctly. Using correct units explain the meaning of this. So this thing from the integral from 10 to 70 of vt dt is, okay, so the antiderivative of velocity is position. So this is accumulating position. It's the total amount of change in position. So total change in position is the total change. And instead of saying position, I mean, we know that we're talking about a rocket and it's being launched upward, so it's total change in height if you want to be even more accurate. But if you say position, you'll get full points. So I'm going to say height because it's slightly more accurate in height. And then that's measured in feet. From 10 to 70, I'm guessing it's seconds, yeah. Our unit up here was seconds, so seconds. Cool, and then use a midpoint Riemann sum with 3 subintervals. All right, so midpoint, everyone got this one correct as far as I remember. From 10 to 70, so don't start at 0, start at 10, and then I'm going to go use those 2 points and choose the middle. So 30 minus 10 is 20, 20 times 22. So you always have to kind of skip every other. It goes like that. So we'll do 30 minus 10, 50 minus 30, 70 minus 50, and then multiply by the height that's in between them. So I think all of these are going to be 20. So we'll say the integral from 10 to 70 of Vt dt is approximated by 20 times 22, 35, 22, 35, and what was the last point? Plus 20 times 44. And of course, you can kind of pull out the 20, so that's the same thing as saying 20 times the quantity of 22 plus 35 plus 44. You could have written this as your first step and you would have gotten full points. You need to somehow show the work though. If you don't show the work, then you're not getting that point, because if you look at the solution guide, you have to actually use V of 20, V of 40, and V of 60. So you have to use these numbers 22, 35, and 44. Then you have to add these up, and I'm just going to look at the answer because otherwise I'm probably going to mess up. So it's 101 times 20, so 2,020 feet. And the reason that it's feet is because it's the total change in height. So it's a total, like the rocket has gone from, well, I don't know what it started at, but it has moved in height 2,020 feet. All right, I think that's all we need to do. Yep, and then we're on to part C. All right, for part C, we're comparing rocket A and rocket B, this new rocket. So this new rocket has the acceleration of this equation. It also has this initial velocity. So it's kind of like the start value. I'll label this start value of 2 feet per second. So initial velocity. Then you figure out which one is traveling faster at time equals 80. Well, let's look at rocket A. So the velocity at time equals 80 of rocket A is going to be given by the table. So if I scroll back up here, the table is 49 at time equals 80. So that's equal to 49. So when we look at rocket B, we have to compare it to that value. All right, so to find velocity is going to be, let's see, it's going to be the antiderivative of acceleration, but we also have to include the start. So it's kind of one of those start plus change deals. I can tell because I know I have to do an integral, so that's change, and I have this start value that I analyze in the problem. So my start is 2, my change is from 0 to 80 seconds, from 0 to 80 seconds of my acceleration function. And I'm going to rewrite this. I don't like fractions and I don't like square roots, so I'm going to say 3 times t plus 1 to the power of negative 1/2 dt. I should also mention that there are 2 different ways of solving this problem. You could instead just find the equation for velocity and then plug in 80. Finding the equation is a little bit different, where you don't have bounds here, and you'll get a plus c, and you'll have to solve for that c using the initial condition. But I think this way is a little bit more straightforward. So when we do this, I have to now, do I use Taxman? Let's see, the derivative of this inner is 1, so I don't need to use Taxman. I can just take the antiderivative. So it's going to be 2 plus, and then this guy is going to be antiderivative. It's going to be 3. And then I'm going to skip some room right here, so, or leave some room. T plus 1, all this to the power of, I'm going to add 1 to negative 1/2, and I get 1/2. Now I'm going to divide down, divided by 1/2 is the same thing as multiplying by 2, or 2 over 1 if you want. And evaluation bar between 0 and 80. Cool. So this thing, just simplifying it a little bit more, it's going to be, that 2 is still out front. I'm not going to touch him. Now I am going to work with this one. So it's going to be 6 times the square root of, and then what goes on the inside. I'm going to plug in 80 first. 80 plus 1 is, I was about to write 80 plus 1. That's the square root of 81. So that was when you plug in the end boundary. The initial boundary is going to be minus, and then it's going to be 6 square root of, when I plug in 0, 0 plus 1 is 1. So there's that. Obviously, square root of 81 is 9. Square root of 1 is 1. And I can simplify this a little bit, so I can write it down here. This is going to be 2 plus the quantity of, I'm going to factor out a 6, so 6 times the quantity of 9 minus 1. 9 minus 1 is 8. 8 times 6 is 48. 48 plus 2 is 50. Alright, so that means rocket B has velocity 50, rocket A has velocity 49. Clearly rocket B is going a little bit faster. So we'll say rocket B is, is traveling faster. At time t is equal to 80. Alright, we're finally on to the review packet. Go ahead and pause the video, read number 3, and if you need to unpause the video now or do whatever, we're on part A. Alright, instantaneous rate of change. So at time equals 10, notice that 10 is in between 8 and 12. So I'm going to do 80 minus 73 divided by 12 minus 8. 80, I don't know what I'm right here, 80 minus 73 is going to be divided by 12 minus 8. So the top I'm going to have 7, the bottom I'm going to have 4, and we need to indicate units of measure. So this is going to be an estimate of a rate, or estimate of your degrees Celsius per minute. So degrees Celsius per minute. We know it's a rate since this has to be divided by minutes. Part B. In part B, we're looking for average temperature. So average of anything. Again, if I'm doing average of anything, it's going to be 1 over b minus a integral of a to b of that anything dt. Yeah, in this case, dt. So we're looking for average temperature. So temperature is going to go inside this box. So it's going to be 1 over, and then 16 is 0. So 16 minus 0 integral from 0 to 16 of my temperature, and temperature is just h of t. H of t, make that slightly curly, h of t dt, and done. That's all we're looking for, just to write an integral. Cool, and now we need to actually estimate this integral using a left Riemann sum with 4 intervals. So again, left Riemann sum means that we have a tail that comes out here on the left. So it's going to be, each of these goes up by 4, which is really nice, which means we can do a shortcut. I'll show you that in a sec. But I'm going to do 4 minus 0, which is 4. 4 times 65. So we'll say now we're approximating. It's going to be 4. And I'm actually going to factor out the 4 from everything. So it's going to be 65. 65 plus 68, 73, and 80. 68 plus 73 plus 80, and each of these is being multiplied by 4. You can think of this as distributed into each of them. And cool, and that just making sure I have the correct number. Yep, 4 sub-intervals, and I just need to figure out what this is. So adding these all together, let's see, what's the quickest way to do this? There's not a really nice way to do this. Let's do just one at a time. So 65 and 68 is 133. I'll write that above here. It's 133. Add 73, and that's gonna go to 210. So 290, and then 290 times 4. But that 4 is technically, all of this is over 16. So this is divided by 16 because of this guy right here. So I'm really gonna be dividing everything by 4. So I'm going to say this is now equal to, what did I say, it was 290. I guess I can check my work on the calculator too. 65 plus 68 plus 73 plus 80. Oh, I was wrong. I feel bad. Okay, well, it was 286. 286 divided by 4, and I believe this is not divisible by 4. But If I divide the top and bottom by 2, I get 143 over 2. And I guess using a decimal, it's going to be 71.5. Again, always check your work. 286 divided by 4. Am I doing this right? Yep, 71.5. And what are our units? Because I believe it says, oh, it doesn't. I'm just going to include units in case there's a question that asks for it. So this is the average temperature. So our units are going to be temperature. So the units of temperature are degrees Celsius. Degrees Celsius. All right, and we're finally on to part C. All right, part C is asking if this answer in part B is an over or underestimate of the average temperature. All right, so we have to look at if we're increasing or decreasing. So 65, 68, 73, yeah, we're clearly increasing. So here's a little helpful guide to remember our rule. I always try drawing like a sine wave, something that looks like this. And we're doing a left Riemann sum. So if I change my color here, I'm using a left Riemann sum, left Riemann sum. And then over here it's going to be left Riemann sum, left Riemann sum. So you can see that when it's increasing, that's going to be an underestimate because there's this area that we're not accounting for. And when it's decreasing, it's going to be an overestimate because we have this extra area that shouldn't be there. So we're going to say that it is an underestimate because we'll say that the h of t is strictly increasing. And usually part C is 2 points, one for saying it's underestimate and one for saying the reason. On to part D. So for part D, we're looking at the table. Is it increasing at an increasing rate? This guy right here. Since we're dealing with a table, we're looking at differences. Just as a bit of a review, can't speak. We'll say h prime instead of f prime. H prime is first differences. First differences. My f's look really bad. There we go. And then h double prime is looking at the second differences. You're just looking at the signs for this one because if it's positive, if this one is positive, then increasing. And this is kind of like the first derivative test. Like if h prime is positive, then the function is increasing. That's the definition that we know. And then obviously, if the second difference is positive, then it's concave up, which is the same thing as saying increasing at an increasing rate. So we're looking at first differences, second differences, and making sure that they're both positive. We don't care what number it is, we just care that they're positive. So coming to this table, I'm going to rewrite these numbers so I can have them with more room. 65, 68. 65, 68, 73, 80, 73, 80, 90. Okay. 90 was bad. There we go. So first differences, I'll do those in yellow. 65 to 68, you're adding 3. You're adding 5. You're adding 7. And finally adding 10. Okay, that was first differences. You can clearly see the first differences are all positive. Now look at the second differences. To get from 3 to 5, from positive 3 to positive 5, you have to add 2, you need to add 2, you need to add 3. Again, second differences are all positive. So you want to say that the answer is yes, it is consistent with the table. The data is consistent with this claim because, I'll write this in red because of the answer. Is consistent with this claim because in both the first and second differences, first and second differences are positive. And that's all there is to it. My F's there need to be a little bit better. Cool. And then we do a little bit of multiple choice, and then after we finish this, you guys can go off on your own for that second piece of paper. Alright, so for each of these, I would appreciate it if you could try to pause the video and think about how to solve this, even if it's for only 5 seconds. I just want you to think about what you're doing. Alright, you've unpaused the video now. We have to use taxman because the derivative of the inner of this 3x is not 1. The derivative of that 3x is 3. So taxman, u is 3x. Taxman, there isn't a taxman out front, so we're just going to say that's 1, and then u prime is equal to 3. We're going to pay this invisible taxman with 1/3, and I now have 1/3 of the integral of cosine of 3x dx. Antiderivative of cosine, anti-change is same sign, so it's 1/3 of the same sign, sine of 3x plus c. Looks like the answer is C. Alright, moving on to number 2. Again, pause the video if you want. And you've unpaused. So I'm plugging in 0. If you plug in 0, you'll notice you get 0 over 0. Whenever you get 0 over 0, there are 3 steps. So whenever 0 over 0, there are 3 steps. Step 1, factor. Step 2, cancel. And step 3, plug in again. Oh, can't spell plug. There we go. Plug in again. So let's factor. The greatest common factor here is, well, it is technically 2x to the power of 3. I'm just going to factor out x to the power of 3 because I noticed that there's not going to be a 2 on the bottom that can factor out. So I'm just going to factor out x to the power of 3, and I'm left with 2x to the power of 3 plus 6. All of this is going to be divided by, again, I can factor out x to the power of 3, and this is going to be 4x to the power of 2 plus 3. Okay, so I just did step 1. Step 2 is to cancel. Boom, boom. That was easy. And step 3 is to plug in again. So again, I'm plugging in 0. So when I plug in 0 here and here, this goes to 0, that goes to 0, and I'm left with 6 divided by 3, which is 2. Alright, we're on to number 4. You're pausing the video, and now you've unpaused the video. So I'm taking the derivative, and this is just Dowder times dinner, so be careful. This Dowder times dinner. So this function can really be rewritten as cosine of 4x, and then this whole thing, quantity to the power of 3. It's just how you write trig functions to powers. So the first thing I do is I bring down the 3 in front, so I'm going to have 3 times the quantity of cosine of 4x, all of that to the power of 2, which means that this 2 is really right there, right? Because that's how you write trig functions. Okay, that was Dowder. And then dinner is going to be a derivative of cosine. So the derivative of cosine is negative sign, so negative sine of 4x, and then there's a dinner inner because 4x has not been taken the derivative of, so the derivative of 4x is 4, so this is going to be times 4. By the way, there are parentheses around there too, in case there's a negative, and that was a really bad multiply symbol. It looks kind of like a minus. There we go. Multiply these all together, and I'm looking at the coefficient. So I have a 4, a negative, and a 3, so my coefficient out front should be a negative 12. So that automatically gives me B. And let's check the rest of it. Cosine squared, yep, 4x, sine x, yeah, everything looks good. So the answer is B. Number 7, go ahead and pause the video. And now you've unpaused the video. So this one, clearly I'm doing something with taxman because otherwise it's not going to work. I have 2 x's. So let's choose taxman correctly. So I can set my u to be, well, it doesn't make sense to set u to x because that's too easy. So I'm going to set it to the inner for the top. Inner for e house is just the power, so u is going to be the square root of x, which again is x to the 1/2. So taxman is, so I'm going to rewrite this one also. So if I bring this x up, then it's going to be, this function is going to be e to the, I guess I'll rewrite everything, x to the 1/2 times x to the negative 1/2. So that's this problem just rewritten. So my taxman is really this guy. Taxman is x to the negative 1/2. Alright, now I need u prime. So if I take the derivative of u, I bring the 1/2 down in front, times the x, but now I'm going to subtract a power to the negative 1/2. And you'll notice that 1/2, or x to the negative 1/2, x to the negative 1/2 cancel out. Chunk, chunk. And I'm left with 1 divided by 1/2. So this is equal to now 1 divided by 1/2, or 1 divided by 1/2 if you prefer that, and just keep it, change it, flip it, which means I'm really going to be multiplying by 2. So taxman, I'm plugging in 2 in the place of x to the negative 1/2. So my new integral now is e to the square root of x times 2. I'll put that out front, dx. And antiderivative of e house is the same, so it's 2e to the square root of x plus c. There it is, a. And that's all I have for the video. I will work on the answer key right now, so I should have that up probably by 6 o'clock a.m. I'm finishing this recording at 5:08 in the morning. Yeah, text me with questions. I'm feeling great. I just have the pink eye, so any questions I'll be pretty responsive to. And I'll see you guys tomorrow.